So tonight we're going to be talking about binary data in Python. It's going to be a high level kind of overview on a lot of stuff, because there's a lot there to go in depth, and we don't have time. So so it's just going to be a quick shallow look. Anytime you got any questions, stop me and go ahead and ask. All right. So first thing to know about the binary data is the bytes type. Bytes is a string-like type, contains a sequence of bytes, as the name implies. It's just a regular built-in class. If we look at the methods, it looks a lot like a string. So, you just got lower, strip, partition, all that good stuff. So to define a bytes object, we can use a literal. That also looks like a string, except we put the B in front of it. That tells Python, this is everything between the quotes, treat it as a byte, each character is a byte. So you can define it with a mixture of ASCII or hexadecimal escape sequences. Any combination of the two works. The escape sequence is just \x and then 2 hex digits, and that defines the byte. You can also, give it. You can also create a bytes object with a list of integers. Each integer in the list is 1 byte. And if we look at this, all 3 of these representations are exactly the same. Iterating over bytes, you can iterate over them. You'll get integers out. 1 integer for each byte. Yeah. Yes. If you try to put an integer over 256, then in this list, it'll throw an error. There'll be like a range error or something like that. I forget exactly what it is. But yeah, so you can define, for these decimal definitions here, you can, any integer between 0 and 256 is valid in this list. Yeah, you're right. It would be to 255. Yep.
Only unsigned values.
Yes, from 0 to 255. Yep. I don't think you can do signed and put signed bytes in there like that. We'll get into later how you could do that. All right, so a binary object is just some blob of data. There's not really a whole lot you can do with it on its own, but it's good. Most of the time it's going to be like a intermediate format, an intermediate type between some data that's stored somewhere or that you're receiving, and and the Python objects that you can actually work on. So let's take a look at how we can convert it to something useful for us in our programs. So we have a byte string here, hello world, and some extra data. This is text data. So Python makes it real easy to convert between some text data that's in some kind of standard encoding and a Python string object. So here we can just decode it using the UTF-8 decode, and we'll get a string out. And the opposite also works. So we load our object. We got the byte representation here for this little emoji in UTF-8, and so we load it into a string. Get hello world smiley there. And then we convert it back to UTF-8. We get the exact same string we sent in, or we can convert to UTF-16, which is this mess here. You know, Python's got like, I don't know, it's got a ton of different codecs you can use, but mostly you'll encounter UTF-8, I think. All right, so that works for text data, but you know, that's only part of, you know, the binary data you're going to encounter. You know, there are other types of files that are, you know, just structured binary data that, you know, are interpreted differently. So to start with, for an example, we will just use this bitmap image. Goes up there. This dog here I found on Google. So we just have a bitmap image file. To load a binary file, you do it exactly the same as you would a text file. You just open it and got it on read. But the difference here is in the mode. We give it this B flag. That tells Python to not try to decode the bytes in the file and give them to you as strings. Just pass the bytes straight through like they are, you know, on the disk. So we open the file, we can read it, and we'll get a bytes object out. And you know, here's the first 500 bytes in the file. So, you know, this doesn't make, you know, this doesn't have any readable text in it really. So, you know, we can't just use decode or whatever. We have to parse it differently. So let's take a look at this, you know, how a bitmap file is structured. You know, bitmap is an old, you know, old image file format, popular in like Windows 95, 98 days. We're just using it as an example because it's a very simple file format, at least for what we're doing. So for a lot of binary files, binary file formats, what you're going to see is at the beginning of the file, there's a header block. It's just a bunch of data there that tells you how to read the rest of the file, like what encoding the rest of the file is using and how to interpret it. So with the bitmap file, the header looks like this. So the first 2 bytes in the file are going to be B and M and ASCII. This is a file signature, just tells us, you know, tells programs this is the bitmap file. Next 4 bytes going to represent a 32-bit integer. You know, 8 bits to a byte, you know, 4 bytes, you know, 32 bits. So that's just going to be the file size. Let's see, we've got 4 bytes unused. 4 byte for the image offset. That's how far from the beginning of the file the actual pixel data starts. So, you know, that would allow you to skip over the header and everything else and just get straight to the image data. Then we got some image info section here. Got the size of this section, which is always going to be 40. That's another 32-bit integer. All of these unsigned, by the way, they're all positive because none of these would make sense as negative values. We got the image width in pixels, image height in pixels, number of color planes. We're not going to worry about that. And, you know, just some other general stuff. Compression, we're not going to worry about that right now either. All right, then, so after all this stuff, we have a color table. We're going to ignore that as well because we're not going to worry about those types of bitmap formats that would use that. And then we have the pixel data, which is the, you know, the raw bytes that make up each pixel in an image. All right, so we've got this header. It's well formatted. We know what it looks like. So what can we do with it, and how can we load it? We're going to use the Python struct module, which is just a convenient way of taking bytes from some buffer or file and, you know, telling Python the format that they're in, and then struct will we'll be able to take them and convert them into the corresponding Python objects. So, for example, here, down here we've got lists of Python objects, lists of Python variables that correspond exactly with what's up here, and here's the format string that interprets it. First thing you're going to see in the format string is less than symbol. This is just telling struct that we're using little Indian integers, which Indianness is just the byte order that a multi-byte integer is stored in. Going into that in depth is probably beyond the scope of this, but if anyone has any questions, you can talk to me afterwards. Yes. I'm sorry? Yeah, I will post the notebook up on the DerbyPy GitHub afterwards. So yeah, if you just, I think it's GitHub/DerbyPy, and you can find it there when I post it. All right, so we just have a little thing there to tell us the Indianness. We're gonna overlook that for now. Then we have 2s. That's the first signifier in this format. That specifies 2 consecutive bytes. We're just going to take 2 bytes out, raw, pass them through as bytes, and that'll be that. That's just going to be a file signature. Next, we've got this capital I. That tells Python, this is a standard width unsigned integer, which is 4 bytes. If you look at the docs in the struct module, they'll tell you, how, what all the specifiers are. You can just look them up there, and how many bytes they are and what Python object you're going to get out. So we got a bunch of I's because we got a bunch of 32-bit integers here. Then we got these couple H's. These represent short integers, which are short unsigned integers, which are just 16-bit integers, 2 bytes apiece. And then more I's to the end of the header. And the header's 54 bytes, so we'll take the first 54 bytes out of that data that we read from the file and pass it in with the format, and we'll get a header. We'll get this header data back, which is a tuple, which is going to have 1 element for each specifier we have in our format string. So here I'm just unpacking the tuple we got back, and you can see, this lines up with what was in the header specification. We just have a bunch of variables. We can check that, what we got. We should execute this first. All right, and so we got out. We check the file signature. It is indeed, or at least it's saying it's a bitmap file. So that's good. And then, you can see that width, for example, was a 32-bit integer, 4 bytes in the file. We can see that struct is converted into a Python integer object that we can use however we would use any other integer. So, here's just some file data. Got the size here. It's about, 800K. Resolution and all that. Bits per pixel, using 24, so that's 3 color channels, RGB, 1 byte each. So each pixel is going to be 3 bytes, 1 byte for each channel. And so now, since we have the pixel data offset, which we loaded from the header, we can pull the pixel data from our buffer and see the data offset was 122 bytes. I guess there's the color palette in between the header and the actual pixel data. Anyway, yeah, we can slice these bytes objects just like strings. That's good to know. Okay, so now we're just going to do some operation, and then we'll do the same thing in reverse, and we'll pack the header back up and save a copy of the file. So I'm just going to invert the colors, do a negative effect on it. So you don't need to really worry about this. Just some binary operations on the individual bytes. It's kind of beyond the scope of what we're doing here. But we're just iterating through it one byte at a time and inverting. All right. So now we'll do the same thing in reverse. Something useful here is the struct calc size. We can pass it the same format string we would use for struct unpack or struct pack. And it will tell you how long the byte string for that needs to be. So, it looks at each individual specifier in the format string and, adds up all the byte widths. And so we're just doing that so we know the total header size, so we know what our offset needs to be. All right, and so struct pack, exact same format string again. That we, same one we used in unpack, but in this case we just pass in arguments, one for each of these specifiers. So we got the file signature. We calculate the file size here, just the length of the pixel buffer and the length of the header. Add them together, zero the reserve field. Total header size with pixel offset, because we're going to just put our pixel data right after the header. Info size, width, height, we haven't changed those. And we're just 24-bit pixels, we haven't changed that. All right, and so, did I run this? All right, so we'll just execute that and we get the header. And we've just packed all the data back into the header. We get struct pack will give us a bytes object back, and this is what it is. So, and now we can open our output file and write it out. Once again, same as if we were working with the text file. Only difference is we have the B in the mode. And you can just write it out. So we just write just pass in bytes instead of strings to the right function. So we write the header and then just write the pixel data right afterwards. And let's see if that worked. Yep. So we got our own bit. We got a inverted bitmap file back out. And yeah, that's how you deal with files. Any questions on any of that so far? All right. Yeah. Okay, so in the file, you just have a byte sequence that's going to be, just the machine representation of the integer. Just the, like you take the base 10 number, convert it to base 2, and those are the bits you have for those 2 bytes. When you take it into Python, if it's in, like all the integer values all load into the same Python integer type. So there's not separate types for, a 32-bit or a 16-bit in Python. Python just has one integer type. Whereas if you were looking at it in C, you would have separate types. For example, in C, you would have the basic int type that would represent the 32-bit. You would have the, short int, which would be the 16-bit, and things like that. Did that answer your question? Yeah. Okay. Anything else? All right, that's most of what I got. Just some other quick stuff. Other ways to encode binary data, if you want to be able to serialize the binary data into some, into some string kind of representation. Say you wanted to embed it in some like JSON document or, an XML document or something. You can encode it. Bin ASCII's got some useful functions in it. You can hexlify on a bytes object and get back, just the hex representation of it. I think it's got a binary version of that. You can get back the actual ones and zeros as a string, that kind of stuff. And of course, it can go the other way and decode it as well. And, there's also base 64, which is probably one of the more common ways to represent binary data in a string format. You've just got B64 encode and decode. And yeah, that's about it. Yes. Yeah, this is all in Python. I haven't imported any modules. I haven't installed anything from pip or anything like that. Struct is, I think all I've imported is struct. And that's built in Python standard library. Yes.
So I wanted to reset or test value of 1 bit infinity. Do I have to ask
as far as I'm aware, you do. I don't know. We can check the struct module if it's got something in there for that. But you can mask and stuff. Like so, you've got. Let's see. Let's do 7 and 2. That's not a good. Yeah. So. Yeah, I mean, you can just use the AND operator to mask and bit shift and stuff. But let me see. So these are all the formats you got. You got a Boolean. Let's see. Yeah, it looks like it only goes down to byte resolution. So if you have like a block of flags in a file format, you would need to pull that block and then mask them individually. There may be some other standard module thing to help you with that. I'm not sure.
Okay.
Yep. No, sure. Yep. Sounds like a niche to me. Yeah. So I mean, some stuff doesn't really work well with string format. Like pixel data. Like there's not going to be, I have a byte, and that's not going to necessarily map to like an ASCII character or even a Unicode character. So the option would be to base 64 encode it, but yeah, then you like increase the file size by like 33 to 66%. I forget which way it goes, how much that is. But yeah, you significantly increase the file size, and then people reading the file not only have to be able to decode your binary format, they also have to decode base 64 first, and then they can decode it. So, yeah, and so it's compactness, and simplicity of the file format. All right, any other questions? All right, thank you.